Okay, so this is section 6.1, Everyday Geometry and Applications. We see the objectives here are we want to understand what points, lines, and planes are. Concepts we want to use are those of parallel and perpendicular lines. We want to understand what angle measure, angle sum, and angle applications are. And finally, we will work with sine, cosine, and tangent functions. We start with our vocabulary, terminology, and how we denote things mathematically. First, we have the point. Points have no length, no width, no shape. So we say that points are dimensionless. A point is denoted by an uppercase letter. So we see we have an example here, point P. P has an uppercase letter. The purpose of a point is points identify a location. All right, next in our list is a line. A line is a collection of points. Lines extend infinitely in opposite directions, and it will always be assumed that lines are straight. So we have curved paths of points and we have straight paths of points. When we talk about a line, it is a straight path of points. Lines are denoted using 2 points from the line. So we see that A and B here are 2 points on the line. And it gets this double arrow bar above it to say it's a line extending in both directions infinitely. So this is line AB. It can also be written as line BA. They are equivalent statements. Next in our vocab is line segment. A line segment is a portion of a line. Line segments are finite. And when we say they're finite, that means they can be measured. To contrast that to a line cannot be measured because infinity is not a number. We cannot measure infinity. So lines have no measure, but line segments do. We name a line segment using the endpoints, and we denote it with a bar over it with no arrowheads. So we can call this segment AB or segment BA. They are equivalent, and when we say they're equivalent, that means they represent the same collection of points. Next is ray. A ray is a half line. 2 important things about a ray is they have an endpoint and they have directionality. Because of that, rays can only be named one way. Ray AB means the ray starts at A and extends in the direction of B. So ray AB can only be named as ray AB. You cannot name it ray BA because that would be an arrow going in the opposite direction. Last on this page is a plane. A plane is a flat surface with no thickness or depth or boundaries. It extends indefinitely in all directions. And again, it says a plane is denoted with an uppercase letter. Most geometry textbooks I have seen say a script uppercase letter because the print uppercase letters for our points, and it's to just help avoid some confusion. Also, planes can be named using 3 points from the plane that are non-collinear. So, naming planes. 1, use a capital script letter. 2, use 3 non-collinear points in the plane. So typically when planes are drawn, they use parallelograms, but they are not finite like a parallelogram. It is understood that their boundaries extend in all directions. The plane is just to give us a surface to work with. And if this plane had points A, B, and C in it, the fact that A, B, and C are not on the same line says that we can name this plane using those 3 points. Or we could put a script letter in there and say, or plane P. Again, generally the print letters are for points and the script letters are for planes. So our next page here, we're looking at segment length. They give us a segment here, and it says that KB is 10 inches, so the distance from K to B is 10 inches. BM is 12 inches, and MC is 13 inches. Because we have 3 segments that are collinear and do not overlap, since we have 3 segments, they are collinear, they are connected at their endpoints, and they don't overlap. We can use what is called the segment addition postulate. And the segment addition postulate basically says that a larger segment, KC, can be written as the sum of smaller segments that we see here. So we can say that KC is equal to KB plus BM plus MC. Now I can replace KB with the 10 that it's equal to, BM with the 12 that it is equal to, and MC with the 13. KC is equal to 35, and this was in inches. So that's an example of how the segment addition postulate works. Let's draw an example where it does not apply. Suppose AC equals 15 and BD equals 17. Does AD equal 15 plus 17? And the answer should be no. The reason for that is that from A to C is here, and from B to D is here, and we have an overlap here. That means we are double counting this length of segment BC. We're counting BC twice, and that is an inaccurate measurement then for AD. So that's what we meant up here. Collinear means that they're in a straight path. So let's look at an example where collinear is the rule that is broken. So since AB is equal to 17 and BC is equal to 13, does that mean that AC is equal to 17 plus 13? Once again, you should tell me no. because they're not collinear. Collinear means they need to be in a straight path. If it was drawn this way, A to B to C, then that would be fine because they're all in a straight path. But we see here in this drawing, AC is actually this path here. AC has nothing to do with AB plus BC. AC is not equal to AB plus BC because not collinear. So we need to have segments that are collinear. They have to be connected, and they cannot, or we say they don't overlap. Those are the conditions we're looking for. And just one last example. So this is read as find the measure of segment AC, and you would say that AC is made up of these segments here, and we'd say, well, then AC is 7 plus 9. And that's fine. They were collinear, they were connected, they were not overlapping. What if I said find the measurement of BE? Once again, you would say starting from B, going all the way to E, all of these segments are connected. We can see that their measurements are talking about non-overlapping segments. 9 represents from B to C, 8 from C to D, 12 from D to E. Again, they're collinear, non-overlapping, and they're connected. So we can say that BE is 9 plus 8 plus 12, which is 29. Okay, so those are some examples of when we can and when we cannot use the segment addition postulate. Next topic is parallel lines and angles. Let's zoom in here a little bit. So if two lines, A, B, and C, D, are in the same plane and they are parallel, then they will never intersect no matter how far those lines extend. And then this is the symbolic representation of how these things are written mathematically. So here this says that line AB, and this symbol means is parallel to CD. Good. Our next term is a vertex. The vertex is the common endpoint between two line segments or two rays. This is the common point of these two figures, so that is the vertex. When we have two segments or rays with a common point known as a vertex, it forms an angle. And immediately we always want to identify the vertex of an angle. And that is because when we name an angle, the vertex must always be the middle letter. So we can name this angle ABC or angle CBA. Again, the vertex is always the middle point, and then you always have a point from each side to wrap the vertex to name the angle. If I put a little m in front of it, that means we're talking about the measure. If I want the measure of angle ABC, then I would expect a numeric value with a degree symbol. If that numeric value is between 0 and 90, then we have an acute angle. So if the measure of angle A is greater than 0 º, degrees and less than 90 degrees. It is acute. Angles could never be equal to 0 degrees because then you do not have an angle. It doesn't exist. And if an angle is equal to 90 degrees, it is not acute. It is a right angle, and that is a vocabulary word further down. So it has to be more than 0, less than 90 to use the word acute. Similarly, if we're talking about obtuse angles, it must be more than 90, less than 180, because 90 is a right angle and 180 is a straight angle. So obtuse has to be in between those two values. And then here we have our right angle, 90 degrees, and you'll generally see a box written in the corner to let us know that's our visual cue that we have a 90-degree angle. And a straight angle is 180 degrees. And then often you'll hear that a straight line is 180 degrees because a straight line represents a straight angle. From here we go on to angle pairs. First we have adjacent angles. Adjacent angles are angles that are next to each other. So we can say that angle 1 is adjacent to angle 2. Or you can say angle 1 is adjacent to angle 4. Again, it's the angles that share a vertex and share a side. So angle 1 and 4 share this side and this vertex. Similarly, we can say that angles 1 and 2 share this vertex and this side. Opposite angles, most textbooks call these vertical angles. Vertical angles are the non-adjacent angle pairs when two lines intersect. So vertical angles, the way that books try to trick us sometimes is they don't draw two lines. Like right here, this is two lines intersecting. 1, 2, 3, 4. 1 and 3 are vertical because they're not adjacent. 2 and 4 are vertical. But here's how books try to trick us sometimes. They'll give us a straight line, and then they'll give us something that's not so straight. In this image, there are no vertical angles. Vertical angles must be formed by two lines. It means you need two straight paths that intersect. And there's no vertical angles because this is a ray and this is a ray. But this is a line up here, and then this is a second line here. There are two straight paths that don't change direction. Where down here we see there are too many changes in directions here. So there's no vertical lines in this one. That's a special case. It's how books sometimes try to trick the learner. All right, so this book's calling them opposite angles. Most other books that I've seen call them vertical angles. The next type of angle pair are complementary angles. If two angles are complementary, that means that their sum is 90 degrees. So the difference between right angle and complementary angle, a right angle is talking about one angle that is 90 degrees. Complementary angles are two angles that add up to equal 90 degrees. Again, with supplementary angles, that means we have two angles that add up to equal 180. If it was one angle equal to 180, we would call it a straight angle. And perpendicular lines, we have here AB and CD. They're perpendicular lines. They form the right angle if they're perpendicular. And once you see that the lines are perpendicular, it means that all four angles are right angles. Once you have one 90-degree angle, all four of them will be if you have two lines intersecting. Let's go on to example 2. It says determine if the following angles are complementary. So the measure of angle ABC plus the measure of angle EDF is equal to 44 plus 42, which is equal to 86 degrees. Since it's not 90 degrees, these angles are not complementary. Example 3, supplementary angles. In the following figure, the road is represented by the line CD. So this is our road. While the trunk of the tree is represented by AB. Tree trunk. The point of intersection of the two lines is labeled at E, right here. Use the definition given in Table 3 to show that angle BED is supplementary to angle DEA. So let's zoom in here. All right, so when we're reading the angles, you should start at point B. Here's point B. We travel from point B down to point D. Down to point E, so from B to E, and then from E to D. So because we were told in the figure, the road represented by the line CD, while the trunk is AB, the point of intersection of two lines is labeled at E. We want to show that they're supplementary. Well, to do that, we can say that CED is a straight angle. And we can even say that angle BEA is a straight angle. Since those two are straight angles, we know that they represent 180 degrees. So let's take my drawing out here. We can say that from here to here to here is 180 degrees. Well, BED is this angle here, and DEA is this angle. So we know that BED plus angle DEA equals 180 degrees, and therefore are supplementary angles. According to the definition. So, definition of supplementary angles are two angles that add up to 180. Even though we don't have exact measurements here, we see that we have a line which forms a straight angle, which means that the two must add up to 180. Example 4, given the figure, find the measure of angle EBD. So again, we start by locating our angle in the drawing. We start at E, we trace along to B, and then to D. So this is our angle that we're looking for. And we know, let me get a different color here, we know that angle ABC is a straight angle. So we can say that angle ABE plus angle EBD plus angle DBC equals 180 degrees. We can see from the drawing that this angle is 90 degrees, that this angle is 37 degrees, and because EBD is unknown, we will call it x degrees. Now we can write our equation, 37 plus x plus 90 has to equal 180. We can combine these two constants and say that x plus 127 is equal to 180. Now we can subtract 127 from both sides of our equation. X is equal to 53 degrees. So we used something similar with line segments before, and we called it the segment addition postulate. This technique here is known as the angle addition postulate. And again, as long as the angles are all adjacent, we can write the sum of the smaller angles is equal to the greater angle. And we can solve problems like this. Skill check number 1. If two angles are supplementary and the measure of one angle, the measure of one of these angles is 113 degrees, find the measure of the missing angle. So a good way to handle this with word problems is to set it up. We have two angles, so let's call it angle X and angle Y. Once they say that it's supplementary, then that means that angle X plus angle Y is equal to 180. That is what supplementary means. If one of the angles is 113 degrees, we can plug that in and say 113 plus the unknown angle has to equal 180. Subtract the 113 from both sides, and we get angle Y is equal to 67 degrees. So find the measure of the missing angle, 67 degrees. Now, when I was looking at your practice problems online through Hawk's Learning, and I put together some practice in the Blackboard as well, the problems weren't this simple. They were a little more involved. So let me give you an example like that so you can set it up properly and be successful at it. So consider two supplementary angles. Where one angle is 10 more than twice the other. What is the measure of the larger angle? So again, you need a plan, and we started this course out with word problems and devising plans. So the first thing we want to consider is we have two angles that are supplementary. Make up your variables. Angle X and angle Y. Those are your two angles. The fact that they're supplementary means that you have angle X plus angle Y equals 180 degrees. Now we need to address our second condition where one angle is 10 more than twice the other. Let angle X equal 10 more than 2 times angle Y. That's 10 more than twice the other. This means that anywhere we see angle X, we can replace it with this expression. So now, instead of writing angle X, I'm going to write 10 plus 2 times angle Y. Then we have the rest of this equation, plus angle Y, and then equals 180 degrees. I have 2 angle Y's here, and I have 1 angle Y here. Altogether, how many angle Y's do we have? 3 angle Y's. Don't forget our 10 that we have to add, and our 180. Now we can subtract 10 from both sides. And this gives us 3 times y equals 170. Y will equal 170 divided by 3. So let's do that math on the side here. So this means that angle y the measure of angle y is approximately 56.7 degrees. And that means that the measure of angle x is going to be 180 minus 56.7 degrees. So the measure of angle x, so what do we have? 123.3 degrees. The question said, what is the measure of the larger angle? This is the answer that we would want to enter. So, your book gave you a simple skill check. We did that. Your textbook exercises actually do word problems like this one I've given you here. And you'll find some of those for you to practice online in Blackboard. I put together homework practice there. And then you'll be able to move on to your Hawks Learning to complete your section assignment. Next in this section, the book talks about longitude and latitudes. The longitude lines connect the North and the South poles together. So these are your longitude lines connecting North and South poles. And we have a longitude line of 0 degrees called the prime meridian. And anything that is positive goes to the east. Positive is east. Anything that is negative goes to the west. Then we have latitude lines, which are used to measure north and south locations on the surface of the Earth. The latitude line of 0 degrees is our equator. Positive latitude lines are north. And negative latitude lines are south. And angles can be expressed in decimal format, but also they can be converted from degrees with decimals to degrees with minutes and seconds. So 30.5 degrees, this 0.5 can be converted to minutes and seconds. And the way it's defined is that each degree has 60 minutes in it. Each minute has 60 seconds in it. And this measurement isn't constant. I don't know why they put that here. We have a formula to use to find the distance between latitude and longitude lines. And because, let me go back, we can see that the distance between here is different than the distance between here. So we have a formula to find these distances. And we see the further north we go, the distance actually gets smaller and smaller till we get to 0. So the fact that they put that in there, I think that's a typo in here because this is not a constant. It shouldn't be in there. So let's do an example where we convert an angle measure from a decimal format to a format with degrees, minutes, and seconds. So 17.78 degrees is 17 degrees plus 0.78 times 60. And this will give us how many minutes we have. So let me get my calculator. 0.78 times 60 gives me 46.8 minutes. Okay, so now I want to know how many seconds is this 0.8. I know I have 46 minutes. So far I have 17 degrees, 46 minutes, which is a single slash, but now I want to take this 0.8 and times 60 to get the number of seconds. So let's clear this out. 0.8 times 60 gives me 48. So 17 degrees, 46 minutes, and 48 seconds is equal to 17.78 degrees. This is the decimal form. This is the degree, minute, second form. So let's do another example. 27.25 degrees. This is 27 degrees plus 0.25 times 60. That gives us 15.0. So we would say that this is equal to 27 degrees, 15 minutes, and 0 seconds. Let's do one more. 198.17 degrees. We have the 198 degrees, that's the whole part. Now let's take the 0.17 times 60. 0.17 times 60 was 10.2. So we have 10 minutes. Now we take 0.2 times 60 to get the seconds. That gives us 12. So 198.17 degrees gets converted to 198 degrees, 10 minutes, and 12 seconds. Here's an example going in the reverse order. So now we want to take it from degree, minute, second form and express it as a degree in decimal. So we start from right to left here. We see that 23 minutes is 23 divided by 60. And 23 divided by 60 gives me 0.38333. So that means that 56 degrees, 26 minutes, and 23 seconds is equal to 56 degrees, 26.383 minutes. This is a decimal of minutes. Now we want to convert this to a decimal of degrees. So we take the 26.383 and divide it by 60. And this is equal to, what was that, 0.4397. So now we can say that this is 56 point, and I'm going to round it to the hundredths place, 44 degrees. Let's do another one. 13 degrees, 50 minutes, and 17 seconds. Let's convert to a decimal. we start from the right-hand side. 17 over 60. That is equal to, where to go, 0.283 repeated. That means that we now have 50.283 minutes. We want to divide this by 60 to get a decimal of degrees. 50.283 divided by 60 is 0.838. And now we can say that we have 13 point, I'm going to round to the hundredths place, 84 degrees. Skill check 2, convert 125.345 degrees to degree minute second format. So we have 125 degrees, and now we have 0.345 times 60. This is 20.7, so we're at 125 degrees, 20 minutes, and now we're going to use 0.7 times 60 to get the number of seconds. 42 seconds. So we have 125 degrees, 20 minutes, and 42 seconds. This is equal to 125.345 degrees. Applications of angles. Here we see in this example we have a rocket that is launched. It is making an angle of theta. This is the Greek letter theta. An angle of theta with the moon that is positioned directly overhead, given that the rocket travels at 18,000 miles per hour and the moon completes a circular orbit with a radius of 240,000 miles approximately every 30 days. At what angle should this rocket be fired so the rocket will intercept the moon? Okay, so one of the first things we have to do is say, how long is it going to take this rocket to travel the radius here? So distance equals rate times time. The distance is 240,000 miles. The rate is 18,000 miles per hour, and the time is what we want to figure out. So 240,000 divided by 18,000 equals time. Let's go to our calculator. And time is going to be approximately 13.33 hours. So now we understand that the moon is moving around the Earth in approximately a circle, so that's 360 degrees. But we want to know the angle theta, and we know that this rocket is going to take about 13 and a third hours to get to the height it needs to get to. But the moon travels this circle around the Earth every 30 days. So we need to convert 30 days to hours. 30 days times 24 hours. $720 hours. So we're going to create a proportion. We don't want to have the moon go all the way around. We want to intercept it right here. So our angle theta over the 360 degrees that the moon travels around the Earth equals 13.33 hours. That's how long it takes our rocket to get up to the altitude of the Earth, over the 720 hours that it takes the moon to revolve around the Earth. And if we cross multiply, 720 times theta is equal to 360 times 13.33. 4,798.8, and now theta equals 4,798.8 divided by 720. And that gives us theta is equal to 6.665 or 6.7 degrees. So if we're looking straight up at the moon, let's erase some of this here. If we're looking straight up at the moon, we should tilt the angle 6.6 degrees, 6.7 degrees away from it so that it will intercept the moon as it's passing overhead. The next application problem we have here is related to GPS. So it says if your location is given in GPS coordinates of 32.75 degrees north, comma, negative 79.98 degrees west, then determine whether you're located in the northern or southern hemisphere, and whether you're located in the western or eastern hemisphere. So I had mentioned on the earlier slide that if your north is you have north and south, and if you're dealing with positive measurements north, then you're above the equator. And if we had positive measurements of east or west, positive means east and negative means west. So we're in the western hemisphere here, northern hemisphere here, and that's because we have a positive and a negative. Positive north, negative south. Positive is east, negative is west. So that was a simple question. It's just understanding the orientation. But next we have what's called the longitudinal adjustment factor. And this has to do with what I was saying earlier, that the distance between these lines is not constant. As you go further north, the distances between them get tighter and tighter, and eventually go to zero when you get to the North Pole or to the South Pole. So this longitudinal adjustment factor helps us determine what is the distance between these longitudinal lines at different measures of latitude. So 69 is the base number that we deal with, and we lose about 4 miles for every degree in latitude measure. So this is the formula that they've come up with, and this is approximate. It's not accurate. You would need or I should say it's not precise. You would need trigonometry to get the precise. They've given us this formula to give us an approximate value so we can approximate distances on the globe. So in this example here, we have Amanda starts at a GPS location of 32.75 degrees north and negative 79.98 degrees west. And they ask how far in miles is Amanda away from her destination, and her destination is at this GPS location of 35.15 degrees north and negative 90.06 degrees west. So really, we have to start by drawing a right triangle. Our start location is here, and this is our start location also. And we see that from 32 to 35 means that we're traveling further north. So if my start location is 32.75 degrees north, comma, negative 79.98 degrees west. So this is my ordered pair for this point. Now I know I'm moving northbound, but after I move north to my 35, how am I moving from negative 79 to negative 90? Well, negative 79 is west of the prime meridian, and negative 90 is further west of the prime meridian. So if we're moving further west, then we're moving further to the left. So this would represent our destination point of 35.15 degrees north, comma, negative 90.06 degrees west. And the purpose of drawing this out is to give us a right triangle to work with, so we can use the Pythagorean theorem. And this triangle exists on a globe. So if we started here and we ended up here, there is a right triangle that represents this triangle that we're talking about. So now that we've got this drawing to help us set up the orientation of the problem, we can now start to do the math with it. How many degrees north did we move? So 35.15 minus 32.75. 35.15 minus 32.75 is 2.4 degrees. And this distance is going to be multiplied by our 69 miles. And the reason for that is, let me get another color here. As we're moving north and south, the distance between the lines does not change. It is when we're moving east and west that the distances change. So this is always going to be 69. But now we want to take our east and west travels and say, how far did we move here? So we went from negative 90.06 minus negative 79.98, negative 90.06 minus a negative 79.98. Oh, something went wrong there. 90.06 minus 79.98, so that's 10.08. So this part of our triangle here is negative 10.08, but now I need to figure out how many miles I'm multiplying by. And to do that, let me go back to my formula. the longitudinal adjustment factor, LAF, is equal to 69 minus 4, and this latitude measure is our destination latitude. And then we divide that by 10. So let's go back to our problem here. Let's find the LAF. 69 minus 4. My destination latitude is 35.15 degrees divided by 10. So my LAF is 69 minus 4 times 3.515. 69 minus 4 times 3.515. Excuse me, that didn't compute. 69 minus 4 times 3.515. .515 times 4. Okay, 69 minus 14.06. For whatever reason, I was not getting that out from the calculator correctly. 54.94. Generally, the book has you just round to the nearest mile, just to keep it simple. We don't need to be precise. They just want you to demonstrate the process. So we're going to say it's about 55 miles in between the lines here where we are located on the globe that we are traveling. And that means we're going to multiply this by 55. So our triangle now, we have 10.08 times 55. So let's clear this all out. 10.08 times 55 is 554.4. And this side of the triangle is 2.4 times 69. That gives us 165.6. And this is the hypotenuse. And to find the hypotenuse, we have to do a squared plus b squared equals c squared. So 554.4 squared plus 165.6 squared equals c squared. .4 times 554.4. What's that? 307, 359. And now we have 165.6 times 165.6. That's 27,423. .307, 359 plus 27,423 gives us 334,782 is our c squared. And where's our square root? 334,782. Oh, there it is. Good. So that gives us that C is approximately 578.6 miles. 578.6 miles. Our next topic is sine, cosine, and tangent. They have a acronym that you can use to remember these. Sine is opposite over hypotenuse. So sine is opposite over hypotenuse. Cosine we see is adjacent over hypotenuse. And tangent is opposite over adjacent. So this gives us this little acronym. Sometimes they just write it this way. And it is pronounced SOHCAHTOA, and those are just the rules for which sides of the triangle you use with each of the trig functions that you're evaluating. So, based on this drawing, everything they said here was sine of A. That means that you put an arc at A because that is your focus angle. And sine of A is the side opposite. That's what's said on top here, over the hypotenuse. So, sine of angle A is equal to the side opposite angle A over the hypotenuse. If we did sine of angle B, it would be equal to the side opposite angle B over the hypotenuse. So you have to label your sides according to the angle that you're focused on. So if we're focusing on angle B, this becomes opposite, and hypotenuse is always the longest side, which is opposite the right angle. If we're looking at tangent of angle B, it is the side opposite of angle B and the side adjacent to angle B. So you always have to put an arc by the angle that is inside of your tangent or sine function, and then label the sides from that angle's point of view. Okay, so here's an example using trigonometry to solve a problem. We see that it says Sam is building a deck on the back of his house. The deck is 4 feet off the ground. According to the building code, the maximum angle for the incline of the steps is 30 degrees, and the maximum length of the steps in the incline is 8 feet. So using the given figure, determine a minimum distance the landing step, which is point A, can be from the house. So if we look at this, we can draw the triangle and say I can solve it either using these two sides, which the angle then is adjacent with x and opposite of 4, or I can solve it, again we need to solve for x, or I can use the 8 feet. So I need to solve this problem twice and see which one's going to give me the better answer, because they're saying what's the minimum distance that I can use here. Alright, so if I look at this left-hand side, adjacent and opposite is the tangent function. So we would say tangent of 30 degrees is equal to opposite, which is 4, over adjacent, which is x. And because we have a fraction, we want to make both sides fractions. I need to get the x out of the denominator, so I'm going to cross multiply. When we cross multiply, we get x times tangent of 30 degrees is equal to 4 times 1. There's our cross product. I'm going to divide both sides of the equation by tangent of 30 degrees. So it cancels, and we have x is equal to 4 over tangent of 30 degrees. I'm going to grab my calculator. When you're doing this, you need to make sure that you have your mode set to degree. Right now it's on radian by default. I've changed it to degree. Now I can type 4 divided by tangent of 30 degrees and hit enter, and we get that x is, what was that answer, 6.928, so we'll say 6.93 feet. and then we'll compare it to the answer from this side. We see that we have adjacent and hypotenuse, so that calls for the cosine function. So we would say cosine of 30 degrees is equal to adjacent over hypotenuse. So now when we cross multiply, we get 8 times cosine of 30 degrees is equal to x times 1. And to solve this, I would go to my calculator and let's clear it. 8 times cosine of 30 degrees gives us 6.93 again. So both answers matched up, and that is the minimum distance that point A can be from the house. Good. All right, let's go to skill check number 3. It says use the Pythagorean theorem and the result from example 10 to confirm that the side lengths form a right triangle. So we have 8 on the hypotenuse, 4 on one leg, and 6.93 on the other leg. 8, 4, 6.93. So 4 squared plus 6.93 squared has to be equal to 8 squared. That's 16 plus 6.93 raised to the second power. 48.025 equals 64. And this gives us 64.025 equals 64. So it is approximately equal, and we would say that yes, it is a right triangle. The measurements are close enough that we would say that is close enough to be a right triangle. All right, example 11. A hiker knows that the distance from point A on a map to another point B is 7 miles. She began at point A and is headed west until she was due south of point B. So she's heading west until she's due south of point B. And is now at point C. So here we are. Okay, she needs to determine her distance from both point A and point B, given that the heading of her route from point A was 46 degrees. From the line between points A and B as shown in the figure. When she arrives at point B, she also needs to know what the angle will be to make her due north route directly to point A. So that last line, they're saying that after she arrives at point B, they want to know what is this angle so that she can return back to point A. Okay, so this problem has a bunch of different questions built into it. So we can first solve for angle B. We see that we have the angle, and from this angle's point of view, this is adjacent and hypotenuse. So we're going to say cosine of 46 degrees is equal to adjacent, which is B, over hypotenuse 7. We write our proportion and cross multiply. So we have 7 times cosine of 46 degrees. B is equal to 4.86. We can also solve for A. So from this point of view, A is the opposite, and 8 and 7 is the hypotenuse. So opposite and hypotenuse means that we're looking at the sine function. Sine of 46 degrees is equal to opposite over hypotenuse. We set up our proportion, cross multiply. And now we can say 7 times sine of 46 degrees gives us 5.04 for A. So right now we have a triangle that looks like this, 46 degrees. It's a right angle, 5.04, 4.86, and we can solve for this angle by taking 180, subtract this 90 degree angle, and then subtract this 46 degree angle, and we get 44 degrees. So basically this problem was asking for us to solve for all of the unknown measures in the triangle. Good. And finally, our last example, we have an application problem. It says that a ship's sonar locates a wrecked ship at 17-degree angle of depression. So angle of depression means that looking from a horizontal, the angle of depression is the angle down from the horizontal. A diver is lowered 105 meters to the ocean floor. So this is where the diver is. How far does the diver need to travel along the ocean floor to get to the shipwreck? So we're just going to simplify this a little bit. 105, this is what we would like to know. This 17 degrees is going to help us find this angle here, because these two angles together are going to be complementary angles forming a right angle. So 90 degrees minus 17 degrees will give us the triangle measurement for this top angle. So now that we know that is 73 degrees, we can say from this angle's point of view, we have opposite and we have adjacent. So we go back to SOHCAHTOA and we say which of these trig functions uses opposite and adjacent. Well, here's the O and the A, so we're going to use the tangent function. Tangent of 73 degrees is equal to opposite x over adjacent, which is 105. We write this as a proportion. We cross multiply. 105 times tangent of 73 degrees equals x. Let me get my calculator. 105 times tangent of 73 degrees gives us 343.4. And this was measured in meters. So you can see that a lot of the problem solving involves drawing out figures to help us make sense of the problem, using formulas that we were given. Watch the video, take notes, pause it, re-listen to things, try the homework, send me questions, and I will try to respond with other videos clarifying your questions.